In this lecture video, we look at the general form of the multiple linear regression model. Recall that the multiple linear regression model is a regression model containing more than one explanatory variable. Even though it's a linear model, we'll see that the general form of the model includes functions of the explanatory variables that can be highly nonlinear. So here's an outline of the material we'll be looking at in this video. We'll first look at the canonical form of the multiple linear regression model. We'll then see that even though this is classified as a linear model, the deterministic part of the model can be nonlinear in the explanatory variables. As a few examples, we'll look at polynomial functions of the explanatory variables. We'll also look at models including cross-product terms of the explanatory variables.
Now, the first thing we'll do is look at the multiple regression model. And so recall from chapter 2 on simple linear regression that a simple linear regression model is a linear regression model possessing a single explanatory variable, a single x variable. A multiple regression model, on the other hand, is a linear regression model that has two or more explanatory variables. And so let's look at an example of this. Suppose that the yield in pounds of conversion in a chemical process depends on temperature and the concentration of a catalyst. A multiple regression model that might describe this relationship is given in equation 3.1. On the left-hand side, we have our single response variable y, that's the yield in pounds of a conversion. On the right-hand side, we have the regression model itself, and that consists of two components. It's got a deterministic component and a random component. The deterministic component consists of beta 0 plus beta 1 times x1 plus beta 2 times x2. The random component is this last term, the epsilon, all right, and that's a random variable. Now, the deterministic component is called deterministic because once we have values for in this case, two explanatory variables, x1 and x2, then the value of that deterministic component would be completely specified. It would be completely determined. But we know that in the real world, when we are experimenting, collecting data, and so forth, that the values of a response variable are not going to be perfectly predicted by a function such as this deterministic component. There are going to be deviations in the response from whatever deterministic component that we have. And so because of that, we need an additional term in the model to allow for that deviation. And that deviation is allowed for by the error term epsilon. Now, in this particular case, the deterministic component is a linear function of the two explanatory variables x1 and x2. And it's linear in these variables because these are first order variables. They're neither are squared and we don't have their product. We'll look at a generalization of this in a few moments, but I just want to point out that that's not the reason this is called a linear regression model. The reason this is called a linear regression model is because the parameters are in the model in a linear fashion. So we're looking at beta 1 and beta 2. Because those are in this model in a linear fashion, that's why this is called a linear model, a linear regression model in particular. All right, we'll see a generalization of this model in terms of the x's and the x1 and x2 in just a moment. But I wanted to just point that out so we can keep that in mind. So in this particular example, again, the deterministic component is linear in x1 and x2. And so as a result, if we think of it, the graph of this function, it's a plane in 3 dimensions. And we can see this on the next slide. And so in the left-hand portion here, we have a possible graph of this deterministic component, which is represented by the expected value of y. All right, that deterministic component, again, is a plane in 3 dimensions. The domain of this function is the x1, x2 plane. All right. And so the response surface is in 3 dimensions, and in particular, it's a plane. Now, the graph on the right-hand side is it's a contour plot of this surface. In other words, these are level lines associated with this plane. And it's created by taking horizontal planes at various values of the response. And if we think about how a horizontal plane would intersect with this response plane, it would, at any given level of a horizontal plane, it would intersect that response plane in a line. So that's what each of these lines corresponds to. All right, it's a line of intersection between the response plane and a horizontal plane at whatever height is specified here in the graph. So 67, 84, 101, and so forth would correspond to heights here on the vertical axis. Now, certainly we can have more than 2 explanatory variables, and in particular or in general, we can have k explanatory variables or k regressors. And the model, the multiple regression model for that kind of for that situation would look like this. And you can see that the only difference between this general representation and the example we looked at is that we have more than 2 explanatory variables. But we still have the same 2 broad components of the model. We have a deterministic component and we have a random component. Now, graphically, in this, in general, the deterministic component is going to be some kind of a surface in k dimensions. And if these are all first order, then it would be a hyperplane, but it doesn't have to be planar. And we can see that here in the next slide. So models that are more complex in structure than what we saw in equation 3.2 can be used by and analyzed by multiple linear regression techniques. So for example, here's in equation 3.3. Let's take a look at the deterministic component of this model. So we have really a single, if we think about the explanatory variable that we have, or that's been collected, we've collected an explanatory variable x. And in this model, we're including a linear component or x, a linear component of x. We're including a quadratic x, and we're including x to the 3rd power. And so if we think about what this looks like, this is not a straight line. All right, this is a 3rd order polynomial in the deterministic component of the model. And so from the standpoint of the explanatory variable x, this is not a linear function. But again, in terms of the parameters, in particular, the coefficients, beta 1, beta 2, and beta 3, those parameters enter the model linearly. Once we have values for x, and then we would have the value for x2 and x3, once those are given, then the parameters here, because they're unknown, they would have to be estimated. And it's from that standpoint that we consider this to be a linear model. Again, when we talk about linear, we're not talking about, or we're not thinking about this as a function of the explanatory variables. We're thinking about it as a function of the parameters that need to be estimated once we have obtained the data. So this is a much more complicated function than a linear function. It's going to be allow us to fit a more complex type of lines and curves and things like that. All right, and we can also see that this can be put back into the representation of that looks more linear if we just let x1 be x, x2 be x squared, and x3 be x cubed. And so it has the same form as the model that we had on the previous slide, but in fact, the curve that is generated by this deterministic component is a 3rd order polynomial. Now, in addition, linear regression models can contain things like interaction effects. And so, for example, suppose that we had collected two explanatory variables, x1 and x2. In addition to the linear components of those two variables, we could include this term here, the product of x1 and x2, as part of our deterministic component. And you can see here that in terms of x1 and x2, that's not a linear function of those two explanatory variables. But if we set x1 and x2 equal to, or rename that as a new variable x3, then we can rewrite it this way, and it has that same general form that we had 2 slides ago. All right, but from the standpoint of being a function of x1 and x2, this deterministic component is not a linear function of the two variables, and in particular, it's not going to be a plane. It's going to be a surface that actually has some twist to it, and so we can think of a plane that is now twisted. All right, and so if we had just x1 and x2 in the model and did not have that product term, then we would have a plane like we saw in the previous example. But the inclusion of this product term, x1 and x2, is inducing a twist to that response surface, to that plane. And so now it's more general than the plane that we started with. And the level curves associated with that twisted plane might look something like this. All right, and so now we have a more complicated response surface that we can use to model the response that we're interested in. So this statement here on this slide is what we were saying just a few minutes ago. So in general, any regression model that is linear in the parameters, all right, in other words, linear in the betas, is considered to be a linear regression model, regardless of the shape of the surface that is generated by that model. And so again, here we have a plane that's been twisted. All right, so that's more general than just a regular plane. We could also have quadratic terms. We could have a quadratic term for x1, a quadratic term for x2, and so forth. And so that would give us even a more general type of surface. Now, this product term, x1 times x2, right, that induces this twist, what this does is cause the effect of x1, for example, on the response y to depend on the value of x2. And conversely, the impact or the effect of x2 on the response depends on x1. And because of that, that kind of a term, that product term, is called an interaction. All right. So an interaction exists when the impact or the effect of one variable on the response is affected by or depends on the value or values of one or more other explanatory variables. All right, and so here's an example where the deterministic component of a multiple regression model has not only, and this depends on two explanatory variables, x1 and x2, in terms of their linear components, but it also has quadratic components for x1 and x2, as well as an interaction term for x1 and x2. And so with this, you can see that you get a very general type of surface. It's got curvature in multiple directions, and there's also twist that's induced by that interaction term. So you can see here that with a multiple regression model, we're not limited to just response surfaces that are linear in the variables. The response surface generated by the multiple regression model itself can be quite complex, all right, and quite flexible, which is good, in terms of modeling responses that may not be linear in the variables that impact that type of variable. But the reason we call this a linear regression model is because the parameters in that deterministic component are in that component linearly.
So that's what I wanted to show you in this lecture video. I'll see you in the next lecture video.